Hopefully this will give you some good ideas about how to solve our polar and parametric free response questions. All right, the first question we're going to look at is from the 2013 BC Calculus test number 2, and free response number 2, sorry. And we're told that the graphs of the polar curves, and remember with polar curves, we are only looking at a radius and an angle. So the graphs of the polar curves r equals 3, which is a circle with radius 3, and r equals 4 minus 2 sine theta are shown in the figure above, and the curves intersect at pi over 6 and 5 pi over 6. And I'm going to go ahead and note where these curves are intersecting. So here we are intersecting at pi over 6, and then back here at 5 pi over 6. So we see where we are intersecting. Now, the first question here tells us that they want us to find this area S, this bounded area that we're looking at. So immediately we see we don't really have a full figure of either shape, so to speak. And also with polar, we need to remember our polar formula to find an area, and that area is 1/2 times the integral from theta 1 to theta 2 of your radius squared d theta. So that's going to help us. And also, again, this r equals 3 is a circle, so we do need to remember the area formula for a circle is pi r squared. Now, very quickly, most students say, well, if I know the area formula for a circle, then, and if I know this radius, so I know that the area of the circle itself is 9 pi. And that would be great if I had the entire circle, but I do not have the entire circle. Notice that I'm missing a small portion of the circle, which is up here. So I have to figure out, well, how much of this circle do I really have? And so I'm going to draw off this point of intersections here and here. And now let's think about, well, how much of the circle do I really have? Well, keep in mind, back at the old unit circle days, back in hopefully Algebra 2, you learned some unit circle values. And if we go up in 30-degree increments, we have pi over 6, and then the next value, if we move up again, we would have pi over 3. That yellow is so hard to see. And then if we move up again, we're going to have pi over 2. And then if we continue on over, we would also have here 2 pi over 3. And then 5 pi over 6. Now the whole point of doing this is, if we notice, we really are dividing up our circle into equal sectors here. Notice you have 1 here, 2, 3, 4, 5, 6 parts of that circle. And so that's going to make it a little bit easier for us to see, well, really, what's the total amount of circles that we have? Total amount of the circle that we have. Well, in this top part here, we have 6 pieces, 6 equal pieces. And on the bottom, we have 6 equal pieces, because again, we could continue on what we did around the unit circle. So there's a total of 12 equal pieces if, again, we go up in 30-degree measures, or pi over 6, however you wish to think about it. But once we notice, we have all of this bottom shaded, so we have at least 6 pieces of the 12. But then as we move on up, notice on the top part, we don't have all those pieces. And I'm going to erase some of this. We don't have everything up here. So we can't say we have a total of 12, but if we go back to the idea of this point of intersection here, and then we have a point of intersection here, and say, well, I know I have 6, we have 7, and we have 8. We have at least 8 parts of the 12, which is going to be, how much is that going to be? It's at least 2/3 of the circle. So I now know that for my area of the circle part, I know the total area is 9 pi, but I also realize I only have 2/3 of that. So I have a total of 6 pi here. Now, well, what about this remaining amount? What about this little portion up here? Well, that's going to be part of our polar. Notice that we are intersecting here to here, so that's where we need our formula for. So the area formula for the polar part is going to be, we have 1/2, and then the integral from pi over 6 to 5 pi over 6 of our radius squared, so that's going to be 4 minus 2 sine theta d theta. And so once we have that plus our 6 pi, that should generate the total area for us that we need. So really, if we put all of this together, we should have 6 pi. Well, if that'll write, that would help. Plus the integral of 1/2. I tend to forget that 1/2. Y'all don't forget that. Pi over 6 to 5 pi over 6. And then of our radius squared. Oh, and I didn't write that up there. Oh my goodness. Hell is going to freeze over. I've messed up. Nah, just kidding. All squared d theta. And so when we type all of this in our calculators, you should get 24.708 for your final answer. So these problems do tend to look a bit intimidating, but if you can separate it out and really focus on what part is the circle and what part is your other polar curve, that will tend to make this a little easier. Okay, for the next part of this problem, we have part B, and in part B, it tells us that a particle moves along the polar curve, r equals 4 minus 2 sine theta, so that at time t seconds, theta equals t squared. I have a feeling that's probably going to be an important part, so I'm going to circle that. Find the time t over this interval from 1 to 2 for which the x-coordinate of the particle's position, position function, is -1. So when I see particle's position, I think back to AB where x at t equals -1. But we have a problem because this is in parametric, x as a function of time, but I'm given polar. Oh no. So I'm going to have to remember some formulas. And one of the formulas that you should have is x equals r cosine of theta. That's going to go back and let us go through and transform from polar to rectangular. So x equals r, well, I'm given r, it's sitting right there, so I'm going to have 4 minus 2 sine theta. That's going to take care of the r times cosine of theta. So now we have to be careful. We're still in theta. So I need to be in time. Remember, I need x at t. I need that position equal -1. So what I need to do is use this information here. Theta is t squared. And so I need to go through and make that transformation. And so what I will have here is my position function now, x at t, equals, and then I still have 4 minus 2 sine theta, but in place of theta, I'm told that that can be t squared times cosine and again t squared, I'm making that transformation. So now I have my position function, and so now I need to know, well, when is x at t equal to -1? Now I need this part, and so I suggest you graph each one and find their point of intersection here, because these are calculator problems. So graph x equals -1, and then graph this other and find their point of intersection. And hopefully you will find that to be when t equals, and let's see, I got 1.428 seconds. Okay, the next part of this question asks us, for the particle described in part B, find the position vector in terms of t, and then find the velocity. Well, we've already found part of the position vector in part B. That was going to be what we wrote, or what we already have graphed, hopefully in our calculators. We found that x at t was equal to, x at t was equal to 4, I'll move my screen, 4 minus 2 sine t squared times cosine of t squared. And now we need to go through and find the y position. And remember that, and I need to go back up here and write that, because it's the formula again that we need. And that was that y is equal to r sine theta. And that's what I'm going to be plugging into down here. And so down here, let's see, my y position, if I plug in that r value, is going to be 4 minus 2 sine t squared times sine of t squared. Because there's my r value, and then I need to make that substitution. So whenever I write my positions, then, and remember here it says as a position vector, so I need to make sure I incorporate my vector notation. And then I'm going to just recopy these values, 4 minus 2 sine t squared times cosine of t squared, comma, and then my y coordinate, 4 minus 2 sine t squared, and let's see, sine t squared. Okay, so there's my position vector. There's going to be my x at t and my y at t. So here is x at t and then y at t. And then we need, that's going to be the position. And now they ask us to find the velocity vector at time t equals 1.5. So we have to go back now and remember that if we have a position function, to get to the velocity, we need to take the derivative, or find the derivative of that. So what we're looking for here, remember this is a calculator problem, so we're looking for x prime of 1.5, comma, y prime of 1.5. That's what I'm looking for here. And when you put these in your calculator, you should end up with the first coordinate being negative 8.072 and your other coordinate being negative 1.673. Okay, and I hope this helps, and do make sure your calculators are set to radians. Sometimes we miss it for some of the smallest things. And do make sure you watch your notation with this. Okay, this next question came from the 2007 free response BC test. And here, very similar to the other question we just worked through. The graphs of the polar curves r equals 2 and r equals 3 plus 2 cosine theta are shown in the figure above. The curves intersect at 2 pi over 3 and 4 pi over 3, and I always would go ahead and note that. To me, that's something to be aware of for sure, especially when we're writing out our formula. So again, I would make that note. We've got 2 pi over 3, and I can't draw the best in the world, so y'all just be patient with me. 2 pi over 3, and the other one at 4 pi over 3. So somewhere like that. Okay. And so we know our points of intersection. That looks terrible. Let me fix that. So 2 pi over, or my gracious goodness, 4 pi over 3, excuse me. Okay, and notice that we are given a polar graph, aren't we? Yeah, r equals 3 plus 2 cosine theta, and r equals 2. And again, remember the r equals 2 is a circle. So typically the first question, let r blah blah blah, find the area of r. I always skim through the problem to find what I need to know straight off. And so if we are finding the area of r, notice aside from this little part right here, this intersection part, all the rest of this out here is our circle. So again, if we knew how much of that circle's area we had, well then we just about got the question answered. So the area of a circle, pi r squared, so we know the area of the complete circle would be 4 pi, but we also know that we don't have all the parts of the circle. And again, I would go back and remember that these values are really coming from the unit circle, and it divides our circle up into 12 nice equal parts. And then notice on this side here, from all the way here to here, that's 6 parts plus, well, I only have one part here of the circle and another part down here, so that's 2 more. I have 8 of the 12, and 8 of the 12 should reduce down to 2/3. So the first part of this, my area is 4 pi, and so I need to think about 4 pi times 2/3 of the area. So I know I have 8/3 pi for the first part. Now to get this other part of the circle, which is going to be really where we're going to use another formula, and that's this portion here, that's the bounded region of this. So the next part, and I would just go ahead and write all of this together, it is a calculator part. So my final area would be 8/3 pi plus, and then I would 1/2, I always forget that 1/2, times the integral from 2 pi over 3 to 4 pi over 3 of my radius squared, which is 3 plus 2 cosine theta, all squared d theta. And that should be my final area here. And if we type all that gobbledygook in the calculator, I don't remember what we should get. Let's see. Looks like we're going to end up with 10.370. Alright, so for part B, a particle moving with non-zero velocity along the polar curve, given by r equals 3 plus 2 cosine theta, has position x at t and y at t at time t, theta equals 0 when time is 0. The particle moves along the curve so that, and so we have an important piece of information right here, so that the rate of change of the radius with respect to time is equal to the rate of change of the radius with respect to the angle, theta. find the value of dr dt at theta equals pi over 3. So again, these are calculator problems. And so I would not write down a tremendous amount here. Dr dt, since these things are equal, then dr over dt at theta equals pi over 3 is going to be the same thing as dr over d theta when theta is pi over 3. And so really you can type this in your calculator then. That's what it's allowing us to do. So if we just find the derivative of r equals 3 plus 2 cosine theta when theta is pi over 3, we should have our answer, which hopefully if we typed it in the calculator correctly is negative 1.732. Now that's the first part of this. Now the next part, and this is the part most students absolutely hate, you have to interpret your answer in the terms of the motion of the particle. So let's think about this. When theta was pi over 3, our radius value at pi over 3, if we look at that, we see that we're going to have a positive value. So let's think about this a minute. When theta equals pi over 3, we have a few things going on here. Well, first of all, when theta equals pi over 3, our radius is positive, but, I'm sorry, we need to use the word and, to apologize, and the rate of change of that radius with respect to time, dr dt, is less than 0. So even though my radius is positive, its rate of change is negative, so that tells me that the particle then has to be moving closer, or the particle is moving closer to the origin. And I feel like that would be enough information there, moving closer to the origin, or the pole, I guess, if you want to think of it that way. It's the same place. So again, when theta equals pi over 3, our radius, and again, you could do just a quick substitution in and see. You're in the first quadrant, so cosine would be positive in the first quadrant, and so that whole value is positive. And the rate of change, which we just found, that's going to be over here. That value is negative. So even though our radius is positive, its rate of change is negative. So it should be shrinking, is a way to think of it. So it's pulling that particle closer to the origin. Okay, for our next question, or part C on this question, the particle described in part B, now we know dy dt equals to dy d theta. Now we need to find the value for dy d theta, dy dt at pi over 3. So very similar to the previous, and then we need to interpret our answer. So we do need to make a few little minor changes here. Again, remember y equals r sine theta, and so we do need to plug in our r value here and find a particular position. Y equals, and then r was 3 plus 2 cosine theta, and that's going to be times sine theta. And so we can type in our calculators, and we know that dy dt at theta equals pi over 3 is really going to be equal to dy d theta at theta equals pi over 3. So we know those are going to be the same, and when we type this in our calculators and find that derivative value, It looks like we got 0.5. We got 1/2 there. And now, so let's think about again what is going on in terms of our y now, or our vertical motion. Well, let's see. When theta is pi over 3, what's going on here? Well, let's see. R, again, would still be positive, wouldn't it? So let's see. Yeah, I would say R is going to be positive, and so all of this is still going to be positive because R was positive and then sine times that. So yeah, our y value here is going to be greater than 0, right? All right, so let's see. Well, if y is greater than 0, and then notice what else we found. dy dt is also greater than 0, is also positive. So here y is positive, our rate of change is positive, so I think it's safe to say that the particle is moving. Let's see, the particle is moving away from, and this is our vertical movement, so it's moving away from the x-axis. Okay, again, this is another problem from BC 2014, so fairly recent problem here on polar area. And for this particular question, it tells us that the graphs of the polar curves r equals 3 and r equals 3 minus 2 sine 2 theta, my goodness, are shown for above between 0 and pi, so I would definitely make note of that. 0 and pi. Let r be the shaded region that is inside the graph of r equals 3 and inside the graph of r equals 3 minus 2 sine 2 theta. Find the area of R. So this is another great area problem. And of course, I always start out by saying, well, how much area of the circle do I have? Because we know very quickly that the area formula of a circle, the area is pi r squared. So let's see. We're given that r is 3. So I know the area part of my circle is going to be 3 squared, so 9 pi, but very few times do I really have the entire circle here. And so we need to look and see, well, how much of the circle do I have? Well, if we go through and look, we really only have this portion of the circle. So it's safe to say we only have 1/4 of that area. So really, of that shaded portion, we only have 9 pi over 4. We only have 1/4 of that. Okay, so now what about for the rest of it? Well, we would need to integrate our radius here. And what about our endpoints? Well, all the others, we've been given endpoints, and they chose not to here. But notice we are starting at 0 degrees, and we're ending up here at pi over 2. So we can use that. And so our total area here, when we put all of this together, is we have 9/4 pi plus, and our area formula would be 1/2 our integral from 0 to pi over 2 of our radius squared, and the radius here is 3 minus 2 sine 2 theta d theta. And since this is a calculator problem, well, all that we have to do now from here forward is just type that all in our calculators, and once you do, you should get the answer 9.708. Okay, so hopefully we're getting pretty good with these types of problems. Okay, for part B on this, we need to find the value of dx d theta when theta equals pi over 6. So let's see, we're given this curve here, but we need dx d theta. So we need to do some converting here. Remember that our conversion is x equals r cosine theta. And so, let's see, oops, got a stray mark there. We have x equals, well, our r value again right here, 3 minus 2 sine 2 theta. There's the r value times cosine theta. And now all I need to do is, in our calculators, we need to know the value of dx dt when theta is pi over 6. And so once we type that all in, we should get negative 2.366. Okay. Now for part C, on part C, we're asked to find the distance between the two curves, and that's going to be between 0 and pi over 2. We need to find that distance between the two. And let's see, well, no, the distance between the two curves, sorry. We need to find the rate at which that distance between those two curves is changing with respect to theta. So this one's a little bit different, but I don't think it's too terrible. If we think about the distance between the two curves, and we're looking from 0 to 2 pi, so we're talking about this distance here, d. So we could define our distance there between the two. I would say that that distance d, we could very easily define that to be my outer r value minus the inner r value. So I would say that that's going to be 3 minus, and then the other r value I have is 3 minus 2 sine 2 theta. Okay, and so let's see here. All right, that I think would be a fair estimate of that distance. And oh, I need to close the parentheses there, or we could just gonna have terrible. And let's see, so that distance should shape up to be 2 sine of 2 theta, looks like. All right, and so now we need the rate of change, don't we? The distance above, find the rate at which the distance between the two curves is changing with respect to theta when theta is pi over 3. And so we can really just type this into our calculators now, I would think, and see if we can find our answer. So let's see, d theta, or dt, I'm sorry, dd, that is weird, d theta, and I want this value when theta is pi over 3, and type that in our trusty calculators, and we should come up with -2. All right, last question. A particle is moving along the curve r equals 3 minus 2 sine 2 theta, so that d theta dt equals 3 for all times t greater than 0. Find the value of dr dt at theta equals pi over 6. So here is the r value. So let's see, dr dt is going to be equal to, if we do the derivative of this, then that's going to be negative, let's see, 2, derivative of sine of 2 theta would be cosine 2 theta times the derivative of our angle times 2. So, and then we have d theta dt. And so let's see, dr dt at theta equals pi over 6 is going to be equal to, well, let's see, that's going to be negative 2 cosine 2 times theta, or 2 times pi over 6 is pi over 3, and then times another 2, and then d theta dt, oh, that's 3, so times 3. And so let's see, we need to simplify this value right here, don't we? So I have negative 2 times cosine of pi over 3 is 1/2 times 2 times 3. And I believe that's sufficient information there. You could stop there for sure. And that should be it for that. That wasn't as bad as I thought it was going to be. Well, that's good. Okay, this next problem, it was from 2005 BC. The curve above is drawn in the xy plane and is described by the equation in the polar coordinates r equals theta plus 2 sine theta. I'm sorry, plus sine 2 theta. 2 sine 2 theta was the last problem. And this is going to be from 0 to pi, where r is measured in meters and theta is measured in radians. The derivative of r with respect to theta is given by this equation here. Well, that was nice. They did the derivative for us. Find the area bounded by the curve and the x-axis. So it's talking about all of this gobbledygook inside here. So it looks like we are going to need to integrate, and we're going to use our nice little handy-dandy area formula. And our endpoints, well, that's going to be from 0 to pi. So we're going to go from 0 to pi of our r. So we have theta plus sine 2 theta. Oh, my marker's not wanting to write today. So sine 2 theta. It's pitiful. I'm going to fix that. That does not look right. So let's fix that right quick. So sine 2 theta, much better, much better. Squared d theta. And so I think that would be it. Just type all of that in your calculator and let's see. So that area is going to be approximately 4.382. Okay, for the next one, part B, we are asked to find the angle theta that corresponds to the point on the curve with the x coordinate -2. So x coordinate, that means we need to go back from polar to our plane, xy coordinate plane. So let's see, we need to go through, because we're talking about our x coordinate, we know x equals r cosine of theta. So let's see, then we need to say, well, then that means x equals, and then in place of r, we know is going to be equal to theta plus sine 2 theta. And then times cosine theta. Okay, and let's see, so we need to know, find the angle theta that happens. So really, this is a graphing calculator problem, so I'm going to set this equal to, I would graph this portion, and then I would graph x equals -2, and I would find their point of intersection. And so when I graph these and I find my point of intersection, it should be at theta equals 2.786. But the biggest part of this, I would imagine, would be remembering this piece here that you had to do that conversion. Okay, for the next problem, let's see, we're between pi over 3 and 2 pi over 3. So we're told, oh, this one's an interesting problem. So we're told that between these two values, dr d theta is negative. So the rate of change of the radius with respect to the angle is negative. So, okay, what does this say about r? And what does this fact say about the curve itself? Well, let's see. If dr d theta is negative, then I would think that if the rate of change of the radius with respect to the angle is negative, then r is decreasing, isn't it? I like to think about this in terms of f and f prime and f double prime, because we know if f prime, just kind of a little bit of a review here, if we know f prime is negative, and so let's review that. If f prime is negative, then we know f is decreasing. Now, decreasing doesn't imply negative. It just means that the value is decreasing. That's all it means. So be careful with that. So that's kind of the idea that I would use down here for this particular problem. So if dr over d theta is less than 0, then it's safe to say that r is decreasing. And so let's see, what does that say about the curve itself? Well, if r is decreasing, then the curve should be getting closer, is getting closer to the origin, I would think. Yeah, closer to the origin. Excuse the terrible handwriting. Okay, so let's talk about this again. Again, we were told that the rate of change of the radius with respect to theta is negative. And they wanted to know, well, what does that mean about r? Well, if the rate of change of r is negative, then r is probably decreasing. And then they wanted to know, well, what does that mean about the curve itself? Well, if the radius is decreasing, then the curve has to be getting closer to the origin. Okay, and last problem of this set. Here we need to find the value of theta in the interval from 0 to pi over 2 that corresponds to the point on the curve in the first quadrant with the greatest distance from the origin, and then we need to justify our answer. When I read through this and I see greatest distance and justify my answer, I think about when we have to talk about a absolute, when we talk about absolute mins and maxes, because this is very similar to that. It really is, because we're looking for a greatest distance here. So really we need to think about, well, where is our r value the longest? Because that's going to be our greatest distance from the origin. And so, goodness, let's see. I would think about, very similar to absolute mins and maxes, I would set up some kind of chart. I have theta, and then I would have my r value. And remember that we do need to test our endpoints. So we do need to think about, well, what happens at 0 and what's going to happen to r at pi over 2. We need to think about those two values. Well, r, let's think about, well, what was r equal to in all this? That was theta plus sine 2 theta, wasn't it? Sine 2 theta. So we can use our calculators, but it's pretty insightful just to plug in 0 here. And we get 0 plus sine of 0, which is all going to be 0. And then if we plug in pi over 2 over here for theta, then that's going to give me pi over 2 plus sine of pi, isn't it? Sine of pi is 0, and pi over 2 as a decimal is 1.5-ish. Let's see, what is it? 5708. Okay, now in addition to always testing our endpoints, then we also had to test our critical points. So we had to also find our critical point. Well, that's where our derivative, our first derivative, was 0. Well, that's going to be where our dr d theta, we need to see, well, where is dr d theta? D theta equal to 0. Where is that going to happen at? Well, if we graph this, and we're given dr d theta, if we graph that and set it equal to 0, or we could just go ahead and say, well, I know 1 plus 2 cosine 2 theta equals 0. Sometimes it's quicker to solve it by hand, but you have to be careful, make sure you don't miss it. So I have something like this, equals negative 1/2. Well, that's going to be over at 2 pi over 3, I would estimate, because we need to be negative, and we're just dealing between 0 and pi. So 2 theta has to equal, this angle here has to equal over in the second quadrant 2 pi over 3, I would expect. And so that means it's going to be at 2 pi over 6, which is just pi over 3. That would be the other value we would need to check. So take your pi over 3 and plug into r. And when you do that, then you end up with 1.913. And so let's see, at which angle, theta, do we get the maximum distance? It's going to be when theta is pi over 3. It happens right here. So theta equals pi over 3. All right. This should be all of the problems that we've looked at in class. If y'all have any questions, please feel free to ask me. I'll be happy to help you.